who remains. I'm going to talk to you and try not to bore you this morning with a little bit of information, or actually a lot of information about facial recognition. So obviously the turnstile guy over there has been sitting in the entryway for some time now. You've probably seen it recognize your face, and if you're kind of lucky, you may have seen it not recognize your face or misrecognize your face. So I kind of wanted to talk. Huh?
How's that lucky?
Lucky in an inverted kind of skewed way. Not very lucky, sarcastic lucky. So I just wanted to talk a bit about some of the technology that sort of undergirds that and try to kind of demystify it at least a little bit. So going to cover a lot of ground, but try to do it very efficiently. So very broad spectrum, but very high level. We're going to talk about a little bit of history. We're going to talk about applications and what you can use it for. Talk about some caveats and things to look out for. And we're going to talk about the future because that's what we do. Opening up with the timeline, someone very smart told me that everyone loves timelines. So here's a timeline. If you really want to go really far back, the sort of history of biometrics can stretch all the way back to like 1879. With computers, it doesn't start till the 60s. And then in recent years, it's just like exploded. And in the last 5-10 years, we've had like really crazy exponential growth. So we're starting to talk about it again in an excited way. So we'll talk a bit about that progression. If you'll bear with me for a second, while we stretch way back to 1876, just to sort of set the stage a little bit. So in 1876, photography had just been invented in like the 1840s. And one of the first uses of photography was to document for criminology, to document things like crime scenes, repeat offenders, known criminals in an area. So police stations were really hot on this new technology of photography, but they had no consistent way of using it or organizing it. So they were just disorganized collections of mugshots in filing cabinets somewhere with no rhyme or reason to it. So in 1876, this guy, Alphonse Bertillon, comes along in Paris, in France. He's Parisian, so I'm probably saying his name wrong. And he's the first person to really standardize this. He basically invents this whole field of study called anthropometry. He kickstarts this whole discussion into how do we look at, measure, and like define and identify the human form in like a really codified, consistent way. So he sort of sets like the canonical mugshot form that we all know today, where you take a picture from the front and a picture from profile. Before it just was willy-nilly. It was, photographs from different angles. But he also sort of codifies this list of measurements, 5 measurements that he says remain consistent throughout a person's lifespan. So like simple things like the length and breadth of the head, the length of your middle finger, actually, and the length of from your elbow to your middle finger. Just 5 primary measurements that remain consistent.
And your ear shape? Ears.
Yeah, he also kind of put out these really weird photographic collections of photographs of body parts. It's kind of neither here nor there, but interesting errata, really morbid and weird to go look through on like a Sunday afternoon. He just has catalogs and catalogs of photographs of like, here's 900 ears, and here's like the differences between all of them. So he really starts to be one of the first people to like pick apart the human form and measure it in a really rigid way. This doesn't come along until 1963. So there's like a century here between kind of the baseline invention of like measuring the human form and the actual computational ability to do it. It starts to kind of trickle in around 1963. This is the year of the JFK assassination. It's also the year where Ivan Sutherland does his Sketchpad demo. So that's the first computerized graphical drawing program, the sort of primordial Illustrator. That's all in 1963. Also in this year, we have this guy, Woodrow Wilson Bledsoe. He's a mathematician. He's a computer scientist before that's really a thing. He's not a president, despite his name. And he puts out this proposal. It's a proposal for a study to determine the feasibility of a simplified face recognition machine. It's really long-winded. It's the proposal for the first paper of its kind. It's the first paper ever to investigate computerized facial recognition. And it's addressed for submission to this mysterious group called the King-Hurley Research Group. You can whip out your phones now and try to Google them if you really want. They don't exist anymore. In like the late 70s, they were revealed to be one of many front research groups for the CIA. So these were fake research groups the CIA would set up to sort of clandestinely funnel money and research into and out of the public sphere. So they were very, very interested in how they might use this new computer technology to track and identify people as early as 1963. But ultimately, it didn't really quite get there. So in 1964, this study comes out. The closest they get is the system where you have an operator sitting there at like an early Wacom tablet, something that came out of Sutherland's research. And they would sit there and they would manually say, here are the eyes, and here's the nose, and here's the mouth, and here's the eyebrows. And they'd manually notate these features. And the computer could give them like a fuzzy, very low accuracy match from like a data set of like 10 people. So really, really limited application and still requires manual input. And they basically conclude that doing this across a large sample set is just beyond the current state of the art, both mathematically, they don't have the mathematical methods to analyze that big of a set of data, and also computationally, right, technologically. So they sort of, in this paper, there's like 4 steps forward, 4 approaches to how this problem can be resolved, right? How do you get to computerized facial recognition? And they talk about a lot of things that will become important, like identifying the whole face at once. So up until now, they'd been looking at individual parts, like, okay, well, what's the difference between eyes, the distance between eyes? What about looking at the whole face and identifying it as a holistic picture? But they also talk about like dividing it up into a sequence of smaller parts and features, and then reassembling those into a face later. Or they talk about approaches where you sort of partition these categories in a way so that you are only looking at the eyes. So they really, the point of this is that they give like 4 wildly varying and sometimes completely different possibilities for how computer-based facial recognition can progress. Number 4 is the really important one. So number 4 is pre-processing to eliminate non-essential variability. And they're talking about pose, they're talking about expression, they're talking about all the things that can change in a face that don't fundamentally change who that face belongs to. And they're also talking about all of the extra information in a picture of a face that a computer doesn't need to identify that face. It's information that gets in the way. And how do you strip that out while just leaving behind the pieces that you need to do facial recognition? So the answer to this problem, the answer to sort of the problem that's been there since the 1960s, and how do you sort of pre-process out this non-essential variability, that doesn't come until decades later in '91. So the pace of development here, we've got like 3 decades between major milestones at this point. And between 1988 and 1991, there's a bunch of really, really smart mathematician dudes who start exploring and putting out papers on this approach called Eigenfaces. And this is huge because Eigenfaces are a way of really compactly representing a face in a way so that you can apply these sort of really complicated mathematical models to actually do facial recognition. You can kind of think of them as like a means of compressing large data sets of faces. This is my attempt to create a somewhat helpful diagram of how this works. It's really quite difficult, actually. So, but the fundamental concept is fairly simple, which is in Eigenfaces, you're taking a huge data set of faces. So you've got pictures of tons of people's faces, and you're looking across them pixel by pixel, and you're just averaging them all together. So from your huge data set of faces, you kind of overlay them all on top of each other, and you create one like face that it's not really a face. It's more like a ghostly, creepy image that's sort of the average of all of the faces in your data set. That's not so special or interesting, but it gets there, I think, because once you have that average image, you can subtract it from all of the others. And when you do that, you go from a really complex representation down to sort of like a Photoshop high-pass filter, like really low-res representation of these faces that still has all the information a computer needs to like identify it, right? So you can see here like a lot of the information has been stripped out, but you can still sort of see like where the main features are, where the eyes are, and where the noses are, where the mouths are. And so you still have the main features you need to do facial recognition and data analysis. So this is just a little art piece from like 2013 that sort of uses that method. I thought this was really cool. So they use that sort of facial averaging method across movies. It's called Portrait. And so they apply it to like The Matrix, they apply it to Kill Bill, to Avatar, to Mission Impossible, all sorts of different movies. And you can start to see like the average face. And they're pretty identifiable. Like I can kind of tell that this is like stylistically The Matrix and this is stylistically Avatar. So it's interesting how you can like strip away a lot of data, but then recombine it and still end up with something that is a face, right? Is a canonical face. You do this enough times, right? You create enough of these like eigenfaces, and where each face is only kind of showing the difference between it and all the other faces. it's really creepy for one, but it also lets you express any input image, any image of anyone's face as some combination of those eigenfaces. So because these eigenfaces only leave behind what's different between images, you can say, oh, it's like 22% of this eigenface, and 10% of this one, and 38% of this one. And if you combine all those eigenfaces together, you get something that looks a lot like Keanu Reeves. This is important, right, because you're able to take like an input image. So I could take a picture of like Mike Godow, and I could overlay him on top of these eigenfaces. And if his eigenface numbers, if his weightings are similar to someone else who's in the database, I can make a match. So if Mike Godow's face is also 10% like this eigenface and 28% like that eigenface and so forth and so on, I can say, this is Mike Godow. So paper comes out in 91, this basic kind of convoluted concept, right? By 1993, the DoD is super psyched about this. Like they're immediately all over it. Instead of the CIA this time. And so they fund this project called Ferret, which is facial recognition technology acronymized in a really weird way. They fund this, this initiative to just like now that the sort of door has been cracked open, right? Now that we have this fundamental technique to like look at faces in a constructive way for a computer to do that, they start pouring money into figuring out the best way to do that. So they start pouring money into facial recognition research. They put out these huge data sets of faces and eigenfaces for people to use and for people to research. So you have the Ferret database for a while to answer that question of where do you actually get those from. And this all sort of culminates, one of the other things they do is they fund like a lot of little competitions. It all sort of starts to come out around 1997. So a couple of years later, these competitions run their course, and you start to see commercialized applications of face recognition software, sort of some of the earliest commercialized applications of face recognition software that's available. This is the first commercially available facial recognition software, at least it's the era of it. It's some of the first facial recognition software to start to use early neural networks, which we'll see again when we start talking about deep learning, right? So it's kind of mimicking the way the brain sees faces a little bit. It gets used by Deutsche Bank. It gets rolled out to some airports, but it still suffers from this fundamental issue of scale, right? So it doesn't end up scaling well across large crowds. It takes people a while to really realize that. They're like, no, it's fine, guys. It's great. It's facial recognition. It works fantastic. This kind of perception and excitement continues all the way through like 2001 and onwards. And 2001 is a really good example of how and why it doesn't scale at this time and why we still have a lot of ground to cover, right? So in 2001, the Super Bowl is held in Tampa Bay, Florida. The police department of Tampa Bay and of Florida in general had been interested for a little while in this kind of emerging technology. They wanted to apply it to policing and to crowd control. And of course, in their brilliance, they think, oh, what better crowd to sort of test this new technology on and see how it does with the crowd than the frickin' Super Bowl, right? Like huge crowds, like let's do it, guys.
And all of them facing forward, or at least
facing in somewhat of a unified direction, right? So they put up cameras around the stadium and they start running people through this facial recognition system, trying to match them against criminal databases. And they do this all without anyone's knowledge or consent. Oops. They don't catch anyone. They don't catch any criminals, no baddies. They catch 14 people who were falsely flagged as baddies by the system, and they detain them briefly and talk to them. Those 14 people file a lawsuit a couple years later with the ACLU. This doesn't bode well, right? It doesn't bode well for the sort of technological ability of the technology at this time, and it doesn't bode well for the cultural acceptance and understanding of it. It's just not, it's bad news bears. And the problem at this time, and even still a little bit today that we'll talk about, is that state-of-the-art facial recognition techniques at that time just couldn't scale to a large crowd. They had to be very specific to a small environment. So you needed these things like a pretty consistent pose, but in addition to that, it became very hard to do this sort of identification across like a huge crowd, because you would start to get these false positives, right? As you start to get a bigger and bigger sample set of people, you're going to run into people who have slightly similar faces to someone else. And things like that, plus things like variations in pose and lighting and expression, which you have a lot of in a big crowd, just totally threw these algorithms like into the bathwater. Like they just didn't work with this sort of scale. So creepy 3D diagram here, you can see early facial recognition tech comes along and fundamentally with some mathematical tweaks is pretty similar for a good decade and a half. But it really only gets you kind of frontal views. You've maybe got a little bit of head tilt, but past that, the methods that are being used to like structurally analyze your face, if you start to go full profile, they don't know what to do, because a face from profile is totally different from a face from front on, right? It's a different mathematical structure to look at. And these sorts of systems, they can't look at those different structures efficiently.
So do you now build bigger data sets, eigenfaces that are side profile?
You can try that. You can try that a lot. But the issue is with eigenfaces, that doesn't work, because eigenfaces are looking for similarities in structure, right, and trying to average those out. And as soon as you turn your face and start including that in your data, it's such a totally different structure that it messes with your averages across the board. So what you really need is this ability to make like deeper guesses and deeper inferences and say like, oh, this sideways face is the same as this frontal face. And that'll come a little later. So on top of the Superbowl debacle, it probably didn't help that around this time, I would say that the public's sort of view of what this technology looked like is a lot like this. You know, a lot of CCTV cameras with big IR blasters. And sometimes, if you're lucky, maybe a little bit like this. So this was a passport scanning machine used by Qantas in the early aughts. And I want to say they only used this for their flight attendants. It wasn't public facing, which I think speaks to sort of the readiness of the technology even then. Either way, not very kind of warm, inviting aesthetics or machinery, right? Like even this guy here, there's a lot of fluorescent lights and like 3 cameras pointing at you. It's like very Minority Report. So just to sort of speak to that like perception at the time, and I think even still now, right? Like there's this cultural perception that you see in culture and you see in art of facial recognition as a tool of surveillance, of sort of this arm of government or policing or something other, something that's not the individual. And it's always looking down at the individual. So this is a piece from recently. It's from 2015. It's by Raphael Lorenzo Hemmer, whom I love dearly. And it's called Zoom Pavilion. And here he's got a big room with like 12 surveillance cameras trained on the room. And as you walk around the room, it's like projecting your face up on the wall and tracking your movement throughout the gallery. So it's like showing you, are you moving closer to someone else? Are you moving farther away? So it's showing both your face and your position relative to other people. So it's sort of this artistic play on surveillance, right? Like making the you very large. But the main problem so far is all these changing variables, like I mentioned, right? It's all the things that change the structure of a face. You need to be able to really make some deeper guesses and some more human level guesses as to like, oh, this face is the same as this one. And you need to be able to kind of have the same sense of perception when we see a face from profile. You know, mentally what we actually do on some level is we kind of rotate it and we go like, oh, okay, I know that that's like Gatto from the side, or I know that that's like Meg from the side. I can see Meg's face in my mind's eye from frontal view, even if I'm looking at her from profile view. We need to get computers to do something very similar. How do we do that? I think that comes with deep learning, which if you want to get technical, is like deeply convolutional neural networks. So this is taking this concept of learning and of sort of neural networks in terms of computers and allowing them to iterate on themselves and make guesses and make inferences and improve their own algorithms, right? So this kind of technology, this is what's used today by Google, by Facebook, by Apple with the iPhone X. It's kind of the standard. It's also what's used on some level in the turnstile over there. So there are a lot of really bad diagrams culled from research papers on how these systems work. This is a really, really, really high-level version that I took a crack at, and we'll go through it kind of step by step. So the first step is to try to fix that pose issue, and to try to feed, you know, at some point you have this box of deep learning algorithms that you want to get to, and you want to feed it a nice clean image that it can work from. So let's use some older methods, right? Let's use some methods that have been around for a bit. First of all, just out the gate, to look at a picture of a face. We've got Will Ferrell. And find some basic landmarks, eyes, eyebrows, nose. We can use those against like the frontal version of those landmarks and we can have the computer do a sort of Photoshop-style perspective warp, right? And kind of warp that image where his head's a little tilted into sort of an approximation of a frontal pose. So it sort of brute forces the pose of the incoming image and tries to guess at and stretch it into like a frontal pose before it passes it into the recognition algorithms so that they have something really clean and consistent to look at. So that step's pretty simple, and that's actually pretty old tech. Where it gets fun and where it gets new is when you start talking about how to recognize that, right? So you've cleaned up the image, now what? This is going to get fun. So to do that, again, at a very high level, you're taking that image and you're feeding it into sort of a box of math and code that is your sort of deep learning algorithms or your sort of convolutional neural network, if you want to call it by the mouthful techie name. So you take this image and you feed it into that sort of box, and ultimately, at the end, what you get out is 128 measurements. What they correspond to, like what points they're actually measuring on Will Ferrell's face, we don't really know. It changes from person to person. It's measuring different points for different people. All we really care about is that this system is designed and trained to give us unique numbers for unique people. So this set of numbers, it's measuring consistent points for every individual, right? So it's going to be different for Gadao. It's going to be different set of numbers for Meg. It's going to be a different set of numbers for Buganim, and those numbers are going to be consistent and unique to each of them.
So regardless of what image of me you submit, you're going to get roughly the same 128 measurements?
Exactly.
For that certain database, I guess, right? For that certain database that you're measuring the face against.
Oh, here's the thing is, and we'll get to that in the next couple of slides, is that it doesn't even really matter at a certain level. Because what you do first is you train a neural network to do this task, and you train it on any large enough data set of images, and then it can do it on any image. It doesn't need to be trained against an image to perform this task, right? So let's actually just jump right into that now, right? You can think when you have these numbers, these 128 numbers, they're kind of like a face key. They're like a numeric ID. So how do you get to facial recognition? How do you train a system to do this? Well, you can imagine that those 128 numbers correspond to points on a graph. Technically, it's a graph in 128 dimensions, but conceptually, that's not relevant, and I won't go there. Let's take 2 images of Will Ferrell to start, and 1 image of someone who's not Will Ferrell. Let's just plug it into that box of math and code with default settings and see what we get, right? So you're just giving it a first go. And you might see on the first pass, or rather the computer would see, because it's learning, right, itself, it would see that the 2 pictures of Will Ferrell and the 1 picture of not Will Ferrell are about equidistant. So that won't do, because what we're trying to do here, tweak our variables and tweak our algorithms just a little bit. And we want to do that until we get to a point where faces of Will Ferrell generate really similar numbers and are really close together on the graph. And faces of people who are not Will Ferrell are really far away, right? So that's sort of the condition we're trying to optimize for. So we add in maybe a little more data. We tweak some variables. Actually, the computer does a lot of this. It tweaks the algorithms and adjusts itself. And it tries again. And Will Ferrells get a little closer. Not Will Ferrells move a little farther away. And it does this over and over and over again, and adjusting its mathematics and adding in a little new training data. And it does this until it's ultimately able to completely optimize for that case. So it optimizes and optimizes and optimizes until it reaches the point where it can't optimize anymore, and that the set of equations that it's landed on, the set of equations it's using, are generating really similar numbers for Will Ferrells, and really dissimilar numbers for not Will Ferrells. Yes?
What's more important, positive examples or negative examples?
What's more important? I would say they're equally important. Because in industry parlance, this is called triplet loss training. You start with a triplet of images, and that's 2 positive anchor examples and 1 negative anti-example. If you take any one of those out, the system doesn't really work. So the 2 positive examples are there for redundancy, right?
I mean, during the refinement process that you're talking about.
Oh, I see. As you start to add in more data. That's really sort of an effect of how the process is going, right? So as you step through that iteration, you might see like, oh, okay, my faces of Will Ferrell are growing closer together, but they're still really close to not Will Ferrells. So I need to add in more not Will Ferrells to sort of nudge the system in that direction. And this is called guided training. It's the part of training these algorithms where you're actually sitting there with a human being kind of directing the course of the output. Does this make some sort of conceptual sense to everyone? Are there any questions before I move on? All right, so
siblings plot really close, and twins and triplets are right there. So siblings will plot very close then.
yes, if they have very similar facial structures, because it's just
And
picking
identical twins will be right over each other.
like right on top of each other, right? Yeah.
But at the end of this process, have you trained an algorithm to identify Will Ferrell, or have you trained an algorithm that can identify anyone?
That is an excellent question, and it's in the next slide. So once you do this with enough people, you do this across a data set. In this case, we're talking tens of thousands of people. So you do this a lot. And once you've done this a lot, you can feed it any image of anyone. It doesn't matter if the system was trained on that. The point is, the system has been trained enough to do this very specific task of looking at a picture of someone's face and measuring 128 unique points, right? That's what it knows how to do. Imagine that we've already run Jon Snow through at some point, right? We've ran him through an initial time and we've labeled him. We've said, this is Jon Snow, this is where he is on the graph for this one picture. We take this image of Jon Snow, we get his numbers, we plot him on the graph, and if we already have Jon Snow somewhere in our system, if we've already said like this set of numbers is Jon Snow, then we can just see that our input image is really, really close to this labeled image of Jon Snow. And again, this comes down to setting thresholds, right? So at some level, you're saying when it's this close, it's close enough. You're looking for the nearest neighbor.
Our thresholds are low, I hope, because I turned out as Peter Burnham.
Our thresholds are like 50%. So if it's like 50 or 60% a match, it's kind of pretty. Yeah. And that's the thing. Sometimes you'll see me when someone walks through and it misidentifies them. I'll go fiddle on the keyboard, and that's usually me lowering the threshold. So a system like this, because it's able to sort of brute force and correct for pose, is able to do it across a much wider range, right? You can do a lot of different poses and expressions. You can have a low resolution image, and it doesn't really matter because a system like this is fundamentally able to make these sort of inferences and guesses that are necessary to identify a face. So that's really cool that we can do that all from a 2D image, right? We don't need any other data. But wouldn't it be maybe a little easier if we had a 3D image? Probably. So enter deep learning plus 3D, really brief section. This is what's used by Facebook and the iPhone X. And fundamentally, it's very similar to what we just talked about, right? The basics of what's happening are there. Really what we're talking about here is that pre-processing step, that normalizing for pose. Facebook, there are no good images of this. If you can find one, I'll give you $10. Facebook does this by looking across their huge data set of faces that they have available to them and basically being able to reconstruct a 3D model of a face from either a single image or a set of images, right? So they infer or guess a 3D model from a bunch of 2D images because they have that kind of data set available to them. And this just means that instead of Google's method where they're kind of like 2D warping an image, they can actually like rotate around a 3D map in space until it's like a frontal pose. So they can take an image of you, project it onto this 3D model of you that they've guessed at, and like rotate that in space until it's at a point where they can recognize it. Kind of weird that they can do that from one or two images. So this is kind of that basic process being applied again in art, again by Raphael Lorenzo Hammer, and again in 2015 because he was very prolific in that year. This is called redundant assembly. And in this, he's just got a bunch of cameras trained on people walking up on this building, looking at their faces from different angles. And he's combining all of those different angles of their faces into one sort of quasi 3D frontal portrait that he projects on the side of this building at large. So he's taking lots of 2D images from different places and turning them into one 3D image. Where this starts to get weird too is if it like picks up someone else who's not you and starts to combine that with your face, you get these weird like meta faces that are like constructed from all these 2D images. Apple with the iPhone X does something very similar, except they just straight up capture an image. Right? They've got dedicated hardware. They capture a 3D image of your face. and they can do all the same stuff, but with a much easier to work with model. Small caveat, or small bonus, I guess, of technologies like this is because you've got a 3D image of the face that you can operate off of and correct for pose width, you can skip a whole step in sort of the facial recognition pipeline. So your actual set of algorithms that do the actual recognition can be a bit simpler, which means they can run on something like an iPhone really efficiently, right? So it's about having, right now we're at this stage where we can do really good facial recognition with 2D and 3D, but 3D right now is a little easier to make work on something like a mobile phone. But I think that research is kind of going to go back and forth for a little bit because we're still in the early stages. So something like this where you have a 3D model, very similar to the 2D in terms of what you can do, only you get a little more pose extension, right? You can go almost full profile and it's still able to tell that it's you. In addition to that, you've got a 3D model of the face, so I can't just like hold up an image, print out of someone's face and have the system say that's them because it's looking for like a 3D model. So technological aesthetic now, right? We've still got a lot of this. I think facial recognition is still associated with policing and government and surveillance. But at the same time, you know, as the sort of pulse of research has shifted from governments to consumer-facing corporations, facial recognition culturally is also this. Like it's like tagging your friends on Facebook you know, during a bathroom break or whenever you do that. I don't know. I don't use Facebook. It's also this, right? It's in your pocket all the time, and it's technology that lets you into your phone, and it's very personal and always on you and embedded. And it's also even just outright silly things like this. So we've gone from it being very technological and very cold to it being something that we use to unlock our phones and put silly faces on each other, right? I think that the kind of perception there is started to shift a little bit. So some applications of this, now that it's like at a good scale, right? Obviously, now that it can work at a little bit of scale, Beijing's looking at rolling it out across their CCTV network and using it mass facial recognition for surveillance. UK is looking at computer vision techniques to track crowds. You can imagine how that might be useful in like protests and things like that. Skipping really quickly through authentication, which we already talked a bit about. These are the more modern passport machines. I think some more interesting applications are things like medical diagnosis. So there's like rare conditions, genetic conditions like DeGeorge syndrome that manifest in distortions in the face and are only common in certain populations. Facial recognition software has been deployed to these populations to help doctors who might not be familiar with what to look for accurately look for and diagnose this genetic disease, right? So you can start to make guesses and inferences that are really useful on top of just who someone is, but also like by the structure of their face or the way their body is, right? This is also used in retail. So Walmart has patents both on using facial recognition to check, to catch shoplifters, either by matching them against a database of known shoplifters or by looking at your behavior. So looking for suspicious body movement and flagging that. They also have patents on using facial recognition to look for signs of emotional distress in self-checkout lines and automatically hail staff for assistance. They haven't really deployed either of these yet, but they're looking very heavily into it. So obviously advertising, like making these demographic assumptions based on a set of faces in terms of age and gender and trying to target advertisements. So if you've got a line full of dude bros standing in line at a Tesco, they might want to maybe have a Twix bar, which is what's advertised here. This is being rolled out in Tesco stores in the UK and tested in Tesco stores. You also have it used for banal things like toilet paper. So the Temple of Heaven in Beijing apparently has a toilet paper problem. They use facial recognition tech to mete out their toilet paper really weirdly, but it speaks to sort of an increasing ubiquity to the tech, right? So some caveats to look out for. We're running short on time, so I'm going to try to be really quick, but let me know if I'm rushing too much. So one, someone has talked about this before. One is how you train and measure these data sets. So in order to train them, in order to measure them, you need a consistent data set to do that against, right? The one that's used right now is called Labeled Faces in the Wild. It's a data set of somewhere in the ballpark of 14,000 images, and it's mostly culled from images of celebrities. So that's important because while that allows for a certain amount of diversity in that training set, if you look at the training set at large, it's pretty clear that it still skews pretty overwhelmingly white male. It's a lot of white male dudes and not a lot of sort of curated diversity. So if you look at the facial recognition systems measured against this metric, Google's FaceNet is here. They do really well. It's like 98.87% accurate, guys. Like totally, like almost 99, almost 100. Facebook's Deepface is like 97.35, really, really close, creeping up. Fisher Vector Faces, which is like the older kind of Eigenface method, that's like 93, right? So if you measure it against this metric, you get some pretty impressive results. But if you measure it against another metric, a more diverse data set or a larger data set, you'll get different numbers. And these numbers can drop substantially down to 75, 50, lower, 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 lower. So that comes into this notion of algorithmic bias, where we assume that the algorithms that run our lives are like totally unbiased and totally rational, but they're not, right? So this is a funny video, or not funny, kind of sad actually, video just showing that in action, where it can't see an African-American face, but it can see a Caucasian-style mask just fine. So some studies that have been done on this have shown that, very few studies, but have shown that there's a persistently lower accuracy rate for African-American faces, 5 to 10% lower, oftentimes even worse. Systems designed in East Asia do better with Asian faces. Systems designed in Europe and the US do better with Caucasian faces. So there's a lot of implicit, often unintended bias built into these data sets and built into these algorithms that we need to be cognizant of, especially when you combine that with their sort of use in policing, right? They're used to sort of generate like algorithmic lineups of people or to make policing suggestions to police departments. Becomes a really big, important issue. So the future, where might it go? Well, in 2016 or 2006, the government did this study. They found in 2006 algorithms for facial recognition were 100 times better than those in 95, or sorry, 100 times better than those in 2002, and 1,000 times better than those in 1995. So extrapolate that out to where we are today. We're continuing to kind of move up exponentially, I would argue, and it's only going to go further and further and further as we sort of trace Moore's law. And one sort of representation of that scale and ability is what size population you can do this across, right? So with Eigenfaces, we were talking about maybe thousands of people. With deep learning, we can do it across tens of thousands. We can do it across our friends on Facebook. Maybe a smallish crowd, but not a huge crowd, right? The future, they're talking about and working at doing it across millions of people. So relevant trend, computers have eyes, right? When you combine that scale with all of these sort of
4 years ago, we started to wonder.
All of the sort of fundamental other inferences you can make from a camera, when fed into a computer. So Amazon Go, right? You walk into the store, you pick up an item, you walk out. Amazon's really quiet on how this works, but it's probably facial recognition, and it's probably or definitely using computer vision technologies to sort of track you as you move throughout the store and tell when you've picked up an item. On top of that, when it's not sure if it's you that picked up an item, it'll look at your previous history of Amazon purchases. So if you pick up an item and the computer sees you do it, but it's not sure if it's ketchup or mustard, it'll look at your Amazon history to say, oh, you like ketchup more, it's probably the ketchup. So it's this layering of information on top of identification that starts to become, I think, really interesting, especially when you pair it with that notion of algorithmic bias, right? It's a lot of information, it's a lot of data, so transparency and trust around that data is going to become explosively important as we start to combine more and more of it, right? We're creating this informational biometric footprint attached to every individual, and it's getting richer and richer every day. I think right now maybe some of us are a little complacent culturally, but I don't know that will last, and I think transparency and trust around how that trove of data is being treated will become more important. I'm glad Macs are robust. So my point there really is that, with a handful of companies really driving the research here and really owning this data right now, how we talk about and communicate and use this technology, which is very powerful and can be used towards positive consumer user experiences, but how we use the data, how we treat it, and how we act as sort of ombudsmen between the users and the corporations and companies and people that own their data. How we message that and how we treat that and how we build in not just this technology into how we design experiences, but also build in around it an ecosystem of trust and transparency around that data becomes a really important holistic viewpoint, I think, to consider, right? You can't just say this technology is really useful and can be used for user experience, you also have to design for the whole ecosystem of what that data being collected is and what that means for the user, right? So that's sort of my call to action, is to be really cognizant of all of that. Are there any questions?